Welcome to NPTEL lecture series, a basic course on electric and magnetic circuits. We are in module 3 on DC transients, lecture 4 is on the step response of RC and RL circuit. In the earlier lecture, we discussed on source free RC and RL circuit. Now, I will go with the source available with the in the presence of RL and RC combination. So, again the corresponding first order differential equation comes into picture, and therefrom we will find the corresponding solution and analyze the RL and RC circuit. We are confined to only the source to be DC, and our in this combination of circuit we have either only RL combination or RC combination, only one storing element will be there. So, we will go by one. So, step response of RC circuit, earlier discussing about discharging of capacitor, now we are talking about capacitor charging. So, we have a capacitor and we have a DC source and a switch and a resistance connected in series R, and a switch is closed at t equals to 0, let us say. So, let the capacitor as earlier also has an initial voltage equals to V naught, and we express them at V 0 minus equals to V 0 plus. It means that because we say capacitor voltage cannot change instantaneously, dV by dt cannot be infinity, earlier have discussed from the very beginning. So, the voltage across the capacitor cannot change instantaneously. It means that whatever was there at V 0 minus, 0 minus means is the voltage across the capacitor just before the switching happens to be at t equals to 0. So, just before the switching whatever capacitor voltage was there, V 0 plus is the voltage immediately after switching. So, at t equals to 0 the switching happened. So, we talk about 0 minus and 0 plus. So, after the switching happens to be there. So, because capacitor voltage cannot change instantaneously, so whatever there voltage was there of the capacitor at 0 minus, same voltage will be there at 0 plus. So, that is the V 0 minus equals to V 0 plus equals to V 0, the initial voltage in the capacitor. For t greater than 0, if you see the circuit, so the circuit is closed now in that sense. So, therefore, we say that the IR resistance current marked in this direction left hand side, and IC as usual entering to the positive terminal of the C. So, that becomes equals to IC plus IR equals to 0, KCL at this node. So, if we substitute the corresponding IC, that equals to C dV by dt, and IR equals to V, the corresponding this voltage V minus Vs upon R, because we have I mentioned the IR from right to left. So, that becomes equals to 0. From this relation, you can write the corresponding dV by dt equals to minus V minus Vs upon RC, and dV upon V minus Vs equals to minus dt by RC, algebraic manipulation. So, integrating this relation, we get natural logarithm of V minus Vs from V naught to V t, that equals to minus t upon RC from 0 to t. So, in time 0 to t after the switching, the corresponding relation becomes like this. If you move further, so this relation becomes natural logarithm of V t minus Vs minus natural logarithm of V 0 minus Vs, V 0 being the initial voltage of the capacitor, that becomes equals to minus t upon RC, and for t this other t that comes out to be 0, t equals to 0 to be comes to be 0 minus t upon RC. So, this gives us natural logarithm of V minus Vs upon V naught minus Vs, that equals to minus T by RC. So, therefore, from there we can write down B minus Bs upon B naught minus Bs equals to e to the minus T upon tau, where tau equals to RC. We know from the earlier example on RC with the source free circuit also, and we have defined the corresponding time constant also. So, therefore, from here this B, the voltage across the capacitor at any instant of time, can be expressed V t equals to, from this relation, V s plus B naught minus B s e to the power minus T by tau for t greater than 0, and for t less than 0 it is V naught. So, the V naught here is nothing but the initial voltage of the capacitor, and that does not change, that is 0 minus and 0 plus, we already mentioned. And afterwards the corresponding voltage across the capacitor becomes V s plus V naught minus B s e to the power minus T by tau. So, what we say here? B s is the corresponding source voltage. So, the exponential term is multiplied with V naught minus B s, and this exponential term with t tends to infinity will vanish, that will give you 0 part. So, that means that finally, the corresponding voltage across the capacitor will be equals to V s, steady state voltage of the capacitor will be V s, because it will behave like an open circuit, no current will flow. So, that is the point, that the steady state voltage of the capacitor is V s. It starts from V naught at t equals to 0 initial voltage, and with an exponential rise in this case it becomes like this, because V s is greater than V naught in this case. So, from the basic loop equation, first order differential equation, we got the expression for V t equals to V s plus V naught minus B s e to the minus T by tau, where tau is nothing but the time circuit, the time constant of the circuit R c. So, what is that R c? From C, if you look at the corresponding circuit, whatever R equivalent comes out to be, that becomes your R, and multiply with C. So, let us have an example. Find the expression of V t for this circuit, same circuit we have to analyze, when the initial voltage across the capacitor is 5 volt, V naught is 5 volt, and the supply voltage V s equals to 10 volt. So, what we say here? We know that the corresponding V t expression happens to be equals to V s plus we say that V naught minus B s e to the minus T by 2, V naught minus B s e to the minus T by tau. So, we say here V s V naught V s e to the minus T by tau, and t less than 0 it becomes V naught, and the corresponding expression here that goes out to be like this, when V s happens to be greater than V naught, V s happens to be greater than V naught. So, starts from V naught and reaches to V s. So, we have an experiment for the transient cases. First, for the R c charging case with source, that you understand. So, we have R and C in series, and this is being switched on with to a voltage source, DC voltage V s. So, for this circuit, whenever you switch on this, as we have already in theory have studied, the corresponding current flows and it charges the capacitor, and the capacitor V c voltage goes on increasing, and in steady state it will reach to the V s voltage. So, this increment in V c voltage goes on exponentially. So, that we like to observe in this through this experiment. So, the objective is to see capacitor voltage transient during a charging in the charging of the R c circuit in the laboratory. So, for that we have the arrangement of a voltage source, a switch, and R and C, and then we measure the corresponding voltage, observe the corresponding voltage on the oscilloscope and record the corresponding voltage, and see that the how does the corresponding voltage across the capacitor changes. We have a demonstration for the R c charging circuit, in which we have a resistance plot, that resistance, and then we have the corresponding capacitance of 10
10 microfarad, resistance of 50 kilo ohm. We have connection like this. This is an RC series circuit, and to this one from a 12 volt battery will energize the circuit. So it is a source connected to the RC circuit case. So for this we will observe the corresponding the transient phenomena on the oscilloscope in this case. For that, I will switch on the corresponding supply, and you see here the corresponding capacitor voltage goes on increasing exponentially, and it settles at this point. Also, it goes to the steady mode in this case. So it starts from this thing, and then after the switching, it exponentially increases and settles at the afterwards.
From the observation in the lab, which record in the oscilloscope, we find the corresponding that plot is shown here. So, the plot shows here that the exponential growth of the corresponding voltage, and it remains steady state after a long duration of time. So, and the theory also have studied that the corresponding steady state close to steady state less than 1% to the steady state value is achieved in 5 tau, and because the corresponding R value is 50 kilo ohm and AC is 10 microfarad. So, the tau value happens to be here 0.5 second. So, the R and C are being maintained with that values. So, then the corresponding tau will be 0.5 second, and the 5 tau here will be corresponds to 2.5 second. So, in this diagram this corresponds to 2.5 second, and this is the corresponding value of the Vs at that time, that of the Vc rather Vc. So, Vc should be equal to Vs in case of the steady state value. So, in 2.5 second for this case it reaches to very close to the Vs value. So, we observe that in this experiment that the voltage across the capacitor increases exponentially from 0, and it reaches to the steady state value that is applied to the voltage Vs. So, now in this case Vs is 10. So, 10 plus V naught is 5. So, 5 minus 10 e to the power minus t by tau. So, this becomes equals to 10 minus 5 e to the power minus t by tau. This is for A, part A. What part B says that we have B part, we have the corresponding initial voltage of the capacitor is 15 volt, V naught equals to 15 volt, and the corresponding source voltage is 10 volt. So, the V naught is greater than now the corresponding Vs, this is the situation. So, for this case the corresponding Vt becomes equals to Vs is 10. So, 10 plus V naught is 15, 15 minus 10 e to the power minus t by tau. So, this becomes equals to 10 plus 5 e to the power minus t by tau. So, what you say here 10 minus 5 e to the power minus t by tau, 10 plus 5 e to the power minus t by tau. In both the expression, what you say that this part, the exponential part, decaying part, so with t tends to infinity, that will vanish. So, this will be 0. Finally, the corresponding steady state voltage of the capacitor in both the case will be 10, that is nothing but the corresponding source voltage. So, the source voltage, the corresponding capacitor voltage in steady state will behave like open circuit, and it will maintain at the corresponding source voltage in this circuit, time constant being same. So, however, we said that one will start at 15 volt, the other will start at 5 volt. So, one in the one case it will be one is increasing, the other case it will be decreasing. So, that is what we say here. First is 10 minus 5 e to the power minus t by tau, the other is 10 plus 5 e to the power minus t by tau, and we have a plot here which shows about these two cases. So, this is for 5 to 10. So, 5 volt this is, to 10 volt this is, and this plot is for tau equals to 0.1 second. Considering a for the plot, I have considered a tau to be R c to be equals to 0.1 second, and the other one is from 15 volt, it comes out and settle as 10 volt. So, these are the two plots if you can see for the perspective. So, this is for the case A, this is for the case B. Another thing we notice here, as already mentioned for the time constant, if we consider the 5 tau, then the corresponding steady state is within range of 1%. So, if you see this 5 tau means this is the corresponding 0.5. So, if you see here, then the corresponding values almost settles to the steady state value. So, this is about something on capacitor charging from a V s greater than V naught and V naught, the other one when V naught is greater than V s. So, in one case it starts from 5 volt and reaches to this one, it starts from 15 volt and reaches to this one. Now, we see that the corresponding V t is V s plus V naught minus V s e to the power minus t by tau. For t greater than 0, the corresponding I c, what happens to the corresponding current I c? Derivative of C dV c by dt will give us that C dV by dt. So, if we take the derivative of this becomes equals to V s minus V naught upon R e to the power minus t by tau. The corresponding happens to be V s minus V naught, V s minus V naught upon R e to the power minus t by tau. So, if you see this V s minus V naught e to the power t by tau, so then this with the exponential term. So, V s minus V naught is a fixed term, V s is given, V naught is given, R is also fixed. So, from there this becomes an exponential term and vanishes. So, it is an like earlier case, in this case also the corresponding current here through this capacitor happens to be decaying like this. Now, when the corresponding capacitor have an initial charge 0, voltage 0, then if we substitute V naught equals to 0, then the V t happens to be equals to V s 1 minus e to the power minus t by tau, and the corresponding I t happens to be V s upon R e to the power minus t by tau. So, the initial rate of the corresponding current in the capacitor charging case happens to be source voltage upon R. So, this is the initial charging when V naught equals to 0, but if V naught is non-zero, then initial rate will be V s minus V naught upon R. So, this is about the overall perspective of what happens to the capacitor charging, the corresponding voltage expression, corresponding current expression, and also for when V naught equals to 0 case also. So, now we can see furthermore have an analysis on this. So, we say that this is about a circuit response. What do you mean by circuit response? Is that the manner in which the circuit reacts to an excitation, like we are applying to a voltage, the response of the R and C combination here, and sometimes we will see also through example also when the change in network condition happens to be there without any excitation change. So, that kind of what is the corresponding response of this one. So, that we like to see this case, that we call it a response in this case. So, in this RC case, charging case, we see that V t equals to V s plus V naught minus V s e to the power minus t by tau for t greater than 0, with V naught equals to the initial voltage of the capacitor. So, this is our complete response of this RC circuit in the presence of source. Then we can divide this to a natural response for forced response, natural response force plus forced response. So, that we call the V equals to V n plus V f, n for natural, f for force. So, the V n equals to V naught part is V naught e to the power minus t by tau, this part is called the natural response, and that is from the stored energy of the capacitor only. This natural response we saw in the case of source free capacitor, source free RC combination. So, at that time only the corresponding capacitor was having certain stored energy and through the resistance is dissipated. Now, that part is nothing but V naught e to the power minus t by tau from this in this relation, and the V f, the force part, is nothing but the corresponding from the source part, independent source part what it happens to be there. So, that becomes equals to V s into 1 minus e to the power minus t by tau. So, in this expression for V t we have two components, one is the natural component, natural response, and the other is the forced response component. So, the natural response is from the stored energy of the capacitor. So, that part is V naught e to the power minus t by tau, and the forced part is V s 1 minus e to the power minus t by tau. So, adding this to V n plus V f, we got the corresponding response to be complete response to be like this. So, we can divide the corresponding response V t equals to V s plus V naught e to the power minus V s V naught minus V s e to the power minus t by tau into two components, natural response plus forced response. The natural component dies down with transient component. This component dies down with the transient component of the forced response, this also the forced response, leaving only the steady state component of the forced response, leaving only the steady state component of the forced response, that is V s 1 minus e to the power minus t by tau. The e to the power minus t by tau will die down, leaving the steady state component, the V s part. So, that we see that V s part will there and this part will vanish, this part will vanish. So, the transient part will vanish, only the V s part will remain in the circuit. Furthermore, this relation again can be also consider expression in terms of two parts, one is the transient part, the other is steady state part. The transient part, temporary part is the exponential decaying part and the steady part is the corresponding permanent part. So, we can tell them in terms of V equals to V t plus V s s, where t for the transient, s s for the steady state part. So, the transient part is V naught minus V s e to the power minus t by tau, this part transient part with the exponential term, and the steady part is this part V s part. So, this also you can express the corresponding complete response of the circuit. So, therefore, we say that the V t equals to V s V naught minus V s e to the power minus t by tau, we can represent in terms of V t equals to V infinity plus V naught minus V infinity e to the power minus t by tau, where V naught is the initial voltage at t equals to 0 plus you understand, if the corresponding switching happens to be at t equals to 0. So, this is 0 minus and this is 0 plus. The voltage across the capacitor does not change instantaneously. So, V naught equals to the initial voltage at t 0 plus if the switching happens to be at t 0, and V naught equals to the final steady state voltage. So, here this is a steady state voltage. So, this is V infinity, V naught is the initial voltage at V naught, that is this is initial voltage and this is again the corresponding steady state voltage V infinity, and this multiply with e to the power minus t by tau. So, therefore, this expression complete response can be represented in terms of the V naught and V infinity. So, the final response of the RC charging circuit, we can for such an RC circuit, we can find the solution for that by using three terms. One, the initial voltage V naught, from there the final capacitor voltage V infinity if it is known to us, and the corresponding time constant R c of the combination. So, if we know these three, then from this relation V t equals to V infinity plus V naught minus V infinity to the minus t by tau, we can find the solution directly without going for the corresponding V s plus V naught minus V s e to the minus t by tau t greater than 0 or t greater than 0 combination, and so that simplifies our analysis for the different circuit. We will see through different examples. So, let us see an example how we can apply the corresponding perspective. So, at t equals to 0, the switch is moved from position 1 to 2. Find the V t across the capacitor for t greater than 0. So, see the circuit. So, the at t equals to 0, the switch is moved from t equals to from the position 1 to 2. So, that is the circuit. So, at t equals to 0, it was in position 1 and then is moved to earlier in position 1, now it is moved to 2. So, as we know that the corresponding circuit solution, we will apply the corresponding circuit solutions. So, we know this corresponding V t, our question is that voltage across the capacitor this. So, V t equals to the corresponding V infinity plus V 0 minus V infinity e to the power minus t by tau. So, as you see here, so V infinity plus V naught minus V infinity e to the minus t by tau, and the corresponding V naught is the corresponding at t equals to 0 plus, and V infinity is the corresponding steady state value. So, what we see here, as discussed earlier for the RC circuit also, we have now two perspective of the circuit. So, first we will find out the corresponding V 0 plus. So, this is from the switch position 1, switch position 1. So, for switch position 1, the corresponding 2 volt, this becomes equals to plus minus 2 volt, and this is switch 1 is closed like this. This is 120 volt, 120 ohm, and this is your capacitor 5 millifarad. The circuit is closed like this. So, now in this steady state, the capacitor acts as a open circuit volt, open circuit condition. So, therefore, the corresponding V naught that becomes equals to 2 volt, V naught becomes equals to 2 volt. So, as the capacitor voltage cannot change instantaneously when it goes from the position 1 to position 2, now we will talk about the position 2. So, this V 0 plus also becomes equals to 2 volt, which will be using in this case, in this relation for the voltage expression. Now, in 2 position, we talk about the time constant tau and the corresponding V infinity, because our circuit becomes now in this 2 position now. So, for the 2 position, it becomes equals to plus minus, this is 5 volt, switches to 5 volt source now. The circuit becomes now 120 ohm, and this is our capacitor of 5 millifarad. So, we see here now the corresponding V infinity becomes equals to, at the capacitor at infinity time will be open circuit. So, this becomes equals to 5 volt straightforward, and the time constant tau in this second case, that becomes equals to R C. So, R is 120 ohm into C is 5 into 10 to the power minus 3 farad. So, this is our time constant for this one. So, using this of V infinity 5 volt, V naught is 2 volt, and the time constant R C from this we can substitute here and get this one. We need V infinity, V 0 and the corresponding tau. So, using that we get the corresponding relations to be like this. So, V infinity is 5 volt, V naught is 2 volt, and R C happens to be 0.6 second. So, this V t becomes equals to 5 minus V infinity minus V naught minus V infinity 2 minus 5, that becomes equals to 5 minus 3 e to the power minus t by 0.6 volt. Now, note that one thing we should learn here, that the R value which we will calculating in many places, what we will see, the R equals to R T H, the Thevenin's equivalent from the corresponding circuit under consideration with all sources with zeroed out, just like the Thevenin's. Simplify the circuit to get the R equivalent and C equivalent. So, what we say that from the C we will look into and we find the corresponding R equivalent or R T H with all sources being zeroed. So, it is just like that corresponding Thevenin's equivalent. Zero means if we have any internal resistance of these sources, we put their resistance, and if it is a voltage source, short it, if it is a current source, it is keep it open. Now, for this answer, what we got from this relation for this expression, we got the corresponding V t to be equals to 5 minus 3 e to the minus t by 0.6. So, let us have a check whether it is about its correctness. So, what we do that, for that we are applying KVL to this loop. Which loop? This loop, because at t equals to 0 this becomes your circuit. this becomes your circuit. So, in this loop we get the corresponding 5, suppose this is the corresponding current I here. So, 5 volt equals to I t into R plus V t. So, this voltage drop in the resistance plus the corresponding voltage across the capacitor is nothing but the supply voltage 5 volt. So, this is about the corresponding KVL. So, thus from the above, if you find the corresponding I t, so I t becomes equals to, so resistance is 120. So, 5 minus this corresponding V t, substitute the value of V t what you have got here. So, then we got the corresponding I t to be equals to 1 by 40 minus t upon 0.6 ampere. So, this from the I t, if you substitute the value from the KVL equation. Also from the relation C dV by dt, so this from the after applying KVL we are getting this current relation. From C dV by dt, which is the basic relation for the voltage across voltage for this. So, I equals to C dV by dt. So, that we got this corresponding I to be equals to, also the differentiating the corresponding voltage across the capacitor, we got to be equals to 0.025 minus t upon 0.6, and these two are same. So, it means that the KVL relation is satisfied for this using this corresponding expression. So, that means that the equation which we obtained by applying this formula is valid. Okay. Furthermore, we will go for more example. Let us say this is the circuit. The switch was at A for a long time. This switch was at A position for a long time, and at t equals to 0 it moves to B. At t equals to 0 it is moved to B. Determine VCT across the capacitor for t greater than 0. So, we are talking about this is our capacitor half millifarad. Find the expression for V C t greater than 0. So, as already mentioned, we have two aspects, because our V t becomes equals to, or V C t becomes equals to, we have the corresponding V c infinity plus V naught, V c naught minus V c infinity e to the power minus t by tau. So, this expression is valid for the t greater than 0. So, we need the corresponding V c naught and the V c infinity. So, for V c naught we need the corresponding circuit condition at A, and for V c naught V c infinity we need the corresponding circuit condition at B. So, therefore, for circuit condition A circuit condition for V c naught, this is the corresponding circuit. So, for this circuit we see here 24 volt source is there, 3 kilo ohm, 5 kilo ohm, and the circuit is closed like this. So, then half millifarad is connected across the 5 kilo ohm. So, at steady state this will behave like open circuit. So, current will flow from here to here only. So, voltage across the 5 kilo ohm we will have to find out. The voltage across the 5 kilo ohm will be 24 volt divided by 5 plus 3 kilo ohm into the 5. So, this becomes equals to 15 volt. So, V c naught becomes equals to 15 volt. Now, we will go to the circuit B position, where we will find the corresponding time constant tau and the corresponding V c infinity. So, V c infinity what will happen now? This switch will be now moving to this. So, this is no more there. So, here the corresponding circuit will now, the capacitor will be exposed to 30 volt. So, in steady state this will be having 30 volt. So, V c infinity becomes equals to 30 volt. And now, the corresponding time constant for this will be R c. The capacitor will see now, because it is connected to B now, 4 kilo ohm into the half. So, this becomes equals to 4 kilo and the half, 4 into half. So, this becomes equals to 2 seconds. So, we got all these things. So, substitute this and multiply this, then we get the corresponding solution in this case. So, as already mentioned, at position A V C naught becomes equals to this becomes equals to 15 volt. So, this becomes equals to, because capacitor voltage cannot change instantaneously. So, this becomes V C 0 plus also. Position B, this tau is R C. So, as I already said that the corresponding combination results like that. So, this is 2 second and V C infinity is 30 volt from this perspective. So, I substitute this and we get this value to be 13 minus 15 e to the minus t by 2 volt. So, this is about the expression for BCT. Now, from BCT you can find out the corresponding current through the capacitor also, a current through the capacitor, current through the resistor, voltage across the resistor, and so all aspect above for t greater than 0. Now, we will see similar to that for the RC about the step response for RL circuit. With RL we see here a source is source excitation. So, earlier I considered for the source free, now we are talking about the with source. So, let us see the circuit. So, if we close the circuit, then if this corresponding current to the inductor is I and this is the voltage. So, we see here this corresponding current I can be expressed in terms of two perspectives, transient and steady state. The complete response becomes equals to transient plus steady state, transient part plus the steady state part, as we have already explained in case of the voltage for the capacitor in RC circuit. So, we know that the corresponding transient part is in terms of A to the minus t by tau. We have seen also in case of voltage relation for the capacitor, also in the RL combination for the source free circuit also, and with tau equals to L by R and A be a constant. On steady state part we say V s by R, because the inductor in steady state behaves like a short circuit. So, that becomes equals to V s by R for the circuit. So, the general expression for the current in this circuit, that becomes equals to I t becomes equals to A to the minus t by tau B s upon R. Let the initial current of the inductor be I naught at I 0 minus equals to I 0 plus, that is the inductor, because inductor current cannot change instantaneously, L di by dt cannot be infinity. So, we say that I plus I 0 plus equals to I infinity equals to I naught. So, at t equals to 0, if we substitute this in this relation t equals to 0. So, this A becomes equals to I naught B s I naught minus B s by R. So, substituting this A value, we got the I t equals to B s by R plus I naught minus B s by R it is minus t by tau. So, this relation is also similar to that. So, if we can say there is expression, this is about the steady state part, this is the initial part, this is steady state part, and this is about the combination of this transient part. So, we can put this corresponding I t equals to in terms of I infinity final value, I naught initial value minus I infinity final value e to the minus t by tau. So, once again this I t, the complete response equals to I infinity plus I naught minus I infinity e to the minus t by tau. This is similar to the voltage relation we got for the RC circuit, V t equals to V infinity plus V naught minus V infinity e to the minus t by tau. Now, note that if we initial current in many cases we will find the corresponding initial current of the inductor to be 0, then our I t becomes equals to V s upon R 1 minus e to the minus t by tau, and to the V L equals to L d by dt you can find the corresponding response of the corresponding inductor current to be that equals to V s e to the minus t by tau also, the voltage of the voltage across the inductor also. So, from this relation we say that like the capacitor case in case of RC, in RL case also the initial inductor current we know, we need to that I naught first part, second part the I infinity the final inductor current steady state part, and third one is the time constant of the circuit, and the time constant is L by R. So, looking from the L we like to find the corresponding R Thevenin and find the corresponding L by R, the time constant at that for the circuit. In the lab, we will see how the corresponding RL transient is observed, is also happen to we see. For this case, we have an R and L connected in series, and we will be connecting to the voltage source through a switch. So, whenever the switch will be closed, the corresponding current through this inductor I will be observed to be increasing, and then in steady states the corresponding current will be V upon R. So, then the corresponding steady state current happens to be through the inductor. So, this current increment from the 0 to the steady state value happens to be in an exponential manner, that we like to observe for a RL with source. So, that is the objective, that the objective is to see the transient current in inductor during source energization.
Now, we will have a laboratory test for the RL switching transient. For this, we have a inductor, air core inductor, and we have a resistance. So, inductance and resistance are connected in series. Also, this corresponding inductor has its own resistance also, and this combination is connected to the supply system. So, the supply, from the supply we switch on the corresponding RL circuit, and then we will observe in the oscilloscope that the how corresponding current exponentially increases from 0 to the steady state value. So, for this I switch on the corresponding source, and then we see that the corresponding transient current increases exponentially, and we will see the expanded version of this corresponding current here. You see here now, from the 0 current it increases and goes to the steady state value, and it increases here in an exponential manner. So, this is what the corresponding RL, in the RL combination, the corresponding current increases exponentially to the steady state value with the switching on the supply.
In the laboratory, the observations we take through the oscilloscope is shown here, same whatever is observed here, and this plot you can see that this plot is for this current increment. So, exponential increment of the current is clearly observed, and if the R value is 4.4 ohm, L is 93.3 millihenry, the corresponding tau happens to be 21.3 millisecond, and 5 tau happens to be 115 millisecond, and in 5 tau the corresponding current is very close to the steady state value, that is V upon R in this case. So, this shows that the corresponding current through the inductor exponentially increases when the corresponding RL combination is switched on to the source. So, in summary, for the RC and RL transients with source, we say that the corresponding Vt equals to V naught plus V naught minus Vt equals to V infinity plus V naught minus V infinity to minus T by tau. For L, we got the corresponding I infinity plus I naught minus I infinity plus e to the power minus T by tau, and this relation we got from the steady state and the transient part of the circuit. So, this is transient part and this is the steady state part. So, in general, whether it is voltage or current, we can express the x current or voltage x infinity, x t 0 plus x infinity e to the minus t minus t naught by tau, where t naught is nothing but the corresponding switching instant. In most of the examples we consider to be t naught equals to 0, however, the t naught happens to be at 3 second, 4 second, 0.1 second, and so accordingly the corresponding shift happens to be there. So, that we have already learned also earlier case also. So, this is generic expression for this. So, whether it is current or voltage. Note that this generic expression is also valid for source free circuit also, because there also we talk about the complete response. The complete response happens to be equals to the corresponding transient response only in terms of that. So, now the question is that the another issue is that another perspective is that the corresponding for the capacitor it is V t and for the inductor is I t, but this is also valid for that. For the inductor also the corresponding V t expression happens to be this, and for the capacitor also the corresponding current expression happens to be the same one. This is from the complete response and the transient part and the corresponding steady state part perspective. So, let us see some examples for the inductor cases also. So, this is a 10 volt source and the corresponding switch is open at t equals to 0, find the corresponding current for t greater than 0. So, in this case we see that we will again find out the corresponding I 0 plus. So, this becomes equals to I 0 minus. For this case the switch was closed. So, that means that the 10 volt source with series with 2 ohm and then the inductor. So, inductor in steady state will be short circuit. So, the corresponding current to the inductor I will happen to be equals to 10 by 2, that becomes equals to 5 ampere. So, this becomes equals to 5 ampere. Now, in the second case when this corresponding switch is open, it means that now the corresponding circuit for tau and the corresponding I infinity. So, the corresponding circuit becomes equals to in this form like this 10 volt, 2 and this is 3 ohm and this is again short, we are talking about the I infinity. So, in I infinity perspective. So, this becomes equals to 3 per 2. So, this we can I infinity, this becomes equals to 10 by 5, that becomes equals to 2 ampere, that becomes equals to 2 ampere. And then the tau that happens to be there, the inductor with this L. So, that L happens to be, so L by R equivalent or R Thevenin's. So, here 3 plus 2. So, L is 1 by 3 and the R is 5 here. So, into 5. So, that becomes equals to 1 by 15 second. Thereby, we say that the corresponding I infinity equals to I naught equals to 5 ampere, I infinity equals to 2 ampere, tau equals to 1 by 15 second. So, writing this expression in terms of I infinity plus I naught minus I infinity e to the minus t by tau, we got the relations to be 5 minus 2 e to the minus 15 t plus 2 ampere. So, this becomes equals to 2 plus 3 e to the power minus 15 t. So, with time t tends to infinity, this will vanish. So, finally, the steady state value will be 2 ampere. Now, similar to what we did for the capacitor also, we can check and see that whether the corresponding KVL, we apply KVL, that is being satisfied or not. So, for this relation with KVL, it is open. So, then the circuit becomes like this. So, for this case 10 equals to IR 5 into I plus LDI by dt. So, now we got the corresponding expression for I, you have already obtained this one. So, if we substitute here, so 5 pi plus LDI by dt, so that becomes equals to, so LDI by dt. So, this becomes equals to this part plus this part and this comes out to be cancelling each other, happens to be 10. So, that means that 5 pi plus LDI happens to be 10. So, it means that the corresponding Kirchhoff's voltage law holds good for this when you take the corresponding current to be this. So, this current is all right. Now, we see here another circuit similar to one, but here the corresponding at t equals to 0, the corresponding circuit, the switch is closed now. Earlier it was open, the switch is closed now. So, we will find again I 0 minus equals to I 0 plus and this for the first circuit. So, in the first circuit it was open. So, then this means that the corresponding I 0 minus, that becomes equal to 10 divided by 2 plus 3. So, that becomes equals to 5 ampere. And then the second case we talk about I infinity. So, that becomes equals to, switch is closed. So, that means that 3 ohm is bypassed. So, then that becomes equals to 5 ampere, 10 divided by 2 will be 5 ampere and the corresponding tau will be now in this case, because this is shorted. So, the inductor will be only seeing one third of the 1/3 Henry and the 2. So, L will be in terms of 1 by 3 and the corresponding 2 into 2. So, this will be 1 by 6 second. So, then you can write down the corresponding expression for I t equals to I infinity plus I 0 plus minus I infinity e to the minus t by tau. So, thereby as I said, I 0 minus equals to 2 ampere, I infinity equal to 5 ampere, tau equals to 1 by 6 second, and in this expression if you write, then you get the expressions to be equals to 5 minus 3 e to the power minus 15 t. So, what we say that anytime we will do these things, two circuits you have to draw, one for this I 0 part and one for the I infinity part, and then from this I infinity and also you can get the tau part for this. So, this is circuit 1, I say it, and this is circuit 2, and this is this circuit 1 and circuit 2 is decided by the corresponding the switch position where it happens to be there. So, that way I can solve the corresponding circuit this. Another circuit, the switch has been closed for a long time, this switch, and it opens at t equals to 0. So, it is open at t equals to 0, find t I t for this. So, again same relation will apply, two circuits as already mentioned we will do, one for I 0 plus, for this case the corresponding inductor current does not change instantaneously. So, I 0 plus equals to I 0 minus. So, for that circuit the switch was closed. So, if you see here this becomes equals to your 5 ohm, switch closed, it is bypassed. So, then this is the inductor. So, in the steady state this will also sorted. So, the current with I, then we have 10 ohm here, and then we have a current source of upward current 6 ampere. So, we like to find the corresponding I here, that is your I 0. So, this I 0 becomes here, you see here. So, this is 10 ohm and this is also short, this is sorted in this manner, this is also sorted. So, this becomes equals to the total current go by this becomes equals to 6 ampere. Second case, now I infinity. So, I infinity means this will open. So, this will be open means 6 ampere will go by this path will be there and it will go by this path. So, then the corresponding I infinity that becomes equals to 6 ampere will be share between in steady state it will be sorted. So, this will be 10 and 5. So, then I infinity will be equals to 6 ampere into 10 divided by 10 plus 5. So, this becomes equals to 15. So, 6 into 10 60 by 15 equals to 4 ampere, that is the corresponding current through this one. And the time constant tau, because this is now open, a time constant tau will be in terms of from this end we will see. So, source will be off. So, now this becomes equals to across this, if you see the if I draw the circuit now, inductor 1.5 Henry and across this is 10 ohm, and again from this case this will be 5 ohm. So, from this if you see the corresponding R equivalent R Thevenin, that becomes equals to 15 ohm. So, then L by R you can find out 1.5 divided by 15. So, that becomes equals to 1 by 1.5 divided by 15. So, that gives you 0.1 second and so. So, thereby we say that the corresponding I naught equals to 6 ampere, I infinity equals to 4 ampere from the two circuits, tau equals to 0.1 second, 1.5 by 15. So, the corresponding I t becomes from this relation becomes equals to 4 plus 6 minus 4 e to the power minus 10 t, that becomes equals to 4 plus 2 e to the power minus 10 t ampere. So, like this we can solve for different combination of R L and so and so. Now, as I already mentioned that the corresponding expression for what we learn here also is also valid for the capacitor discharging case also. So, this example we studied in case of capacitor discharging case, simple example. So, we say that the VCT equals to V naught e to the power minus t by tau, t by R c, and the expression R c here becomes equals to 1 by 3 9 plus 6 15. So, that becomes equals to VCT becomes equals to 10 e to the power minus t by 5. So, R into C 15 into 1 by 3, that becomes equal to 15 into 1 by 3. So, tau becomes equals to 5 second. So, we got this relation to be like this. So, now we will apply the corresponding relation, this relation for this source free case, VCT equals to VC infinity minus plus VC naught minus VC infinity e to the power minus t by t. So, this is final, this is initial. So, we know that the corresponding expression we talk about VCT equals VC naught equals to 10 volt and VC infinity equals to 0, we know that steady state the Vc infinity to be 0 and tau equals to 5 second RC. So, substitute the value, we got this to be 0, then this is 10, this is minus 0. So, 10 minus 0 e to the minus t by tau, that we got to be 10 e to the minus t of 5 second, t minus t by 5 volt. So, same relation we got applying this relation also. So, what we like to say that this is generic equation for voltage for RC, RL and so, and similarly current expression happens to be same also for all combinations, whether it is source free, whether it is with source, and so for all cases we can apply this generic equation, and this simplifies our analysis to a great extent. So, this is we saw in this lecture about the step response for RC and RL circuit, and we generalize the corresponding solution perspective with the relations as mentioned, like V t equals to, for the capacitor case or inductor case, equals to V infinity plus V naught minus V infinity e to the minus t by tau. Thank you.